Hello! So, in this video, we're going to be doing Riemann's rearrangement theorem, which in the book that we're using, at least when we're recording this, the author doesn't present it by name, but that is the actual name of the theorem. So, when we started this whole unit, I started off by giving an example of a seemingly intuitive sum, infinite sum, and giving seemingly intuitive ways of arranging that sum to get four completely different answers, right? And so that motivated a lot of this effort going in about all the rigor and stuff needed so that we knew what the answer was supposed to be. So Riemann's rearrangement theorem, and yes, that Riemann, like the sum and the integral guy, this theorem sort of encapsulates that necessity and sort of is a way of showing you that it is, even though it seemed like it was bad when I was like, oh, you know, this is four different ways of getting a sum, it is so much worse than it seems. So what Riemann's rearrangement theorem says is that if we have some series an and it converges conditionally, which is key here, so remember, converging conditionally means that if we take the absolute value, it diverges, right? If we take the absolute value of each term, it diverges, but if we do it just as is, it converges. So there's some sort of cancellation happening where we have the negative parts getting infinitely large, the positive parts getting infinitely large, but as we add them in order, they're keeping each other sort of small enough that it never actually diverges, right? So if we have one of these conditionally convergent series, and we can fix any value we want that's a real number, okay? And we really mean any, like pi squared minus e, we could do that, right? Fix anything you want. Then there's some rearrangement of these terms, which if you remember rearrangement, we did these bijective functions, right? So when we say there is a rearrangement, what we mean is there's a bijective function such that when we apply it to the index, we get a new ordering. So there's a rearrangement of this thing such that that series, honest to God, 1 to infinity, sums to that real number. So essentially what this theorem is saying is if you have a conditionally convergent series, you can rearrange it to equal whatever number you want. You want it to equal pi, we can rearrange it to make pi. You want it to equal e squared over 17, we can do that, right? You want it to be sine of 4 radians, we can do that, okay? Strictly speaking, this theorem actually goes a little bit further than that. It says that not only can you do this, but you can actually even show that you can rearrange it so that it diverges to positive infinity or negative infinity. And moreover, you can actually arrange it so that not only does the limit not exist, but it doesn't exist by oscillating between any two real values you want it to. So you can sort of have it oscillate between any two fixed numbers, let alone converging to one. So the full theorem is even worse than this, even worse than you thought, but we're just going to sort of pull back and do just this one right here, okay? So just to be real clear then, so I'm going to be tackling this proof, but the idea here is that I want to come up with a bijective function, a way of rearranging these things so that I get that the sum is going to be x. But it has to be bijective, meaning I have to use all of the original an's. They all have to appear somewhere, and I can only use each of them once, right? So it's not like I can just inject random numbers in there. I have to use the sort of abstract things I'm given to somehow get this result, okay? All right, so let's start with that, or start our proof. So, as promised, I'm going to use the an plus and an minus notation, but I'm going to define them here just to be sort of safe that we're all on the same page. So define an plus to be an plus absolute value an over 2, which is really just an for when an is greater than or equal to 0, and 0 for when an is less than 0. Okay. I'm also going to define an minus to be an minus absolute value of an over 2, which is sort of what you would think. Again, to be clear here, I'm using the more standard version of this, not the not the author's version of this, which is to say this thing is actually going to be a negative value, right? Because if an is a positive value, it'll be that minus itself, so we'll get 0 for an being greater than or equal to 0. And if an is negative, I'm going to get negative minus the absolute value of that negative, so I'm going to get 2 times the negative over 2, so I'm going to get an back, which is the honest value of an. I think did I misspeak? No, I said that right. Yeah, it is the negative version. So this is a negative number because this is when an is less than 0. Okay. Now, I think for the sake of clarity in the actual proof, I'm also going to, without loss of generality, I'm going to suppose an is not equal to 0 for any n. So if I'm adding 0, it's not going to be doing anything, right? And if I have to address where it equals 0, it makes the notation and the little nitty-gritty technicality parts one of those alphabet soup things that's harder to follow. So I'm just going to assume it's not 0 just for the sake of how it will be presented. If it is 0, then you could just inject them wherever, like, make the even indices 0 until you run out, and then proceed whatever, right? So, all right. So I'm going to observe a couple things here. So first, a series of an plus, and going from 1 to infinity. So if I add just the positive things, this is going to increase to infinity. And if I add just the negative things, this is going to decrease to negative infinity, right? So again, an is all positive values or 0, except it's 0 where the an would be non-zero, right, would be negative, and it's going to be positive wherever. So I'm adding up a bunch of positive values and the occasional 0 where the an originally was negative. The an minuses, right, these are 0 anywhere an was positive and the negative value wherever it was actually negative. So as I'm adding them up, I'm adding only positives and zeros, so it goes up. This is adding only negatives and zeros, so it's going down, okay? But notably, it's not strictly monotonic, right? It's not strictly decreasing or increasing, it's weakly, right? It's getting no smaller, no bigger. Okay, so I'm going to observe that. I'm also going to observe, so this is because the ANs, right, I mentioned this at the beginning, it's conditionally convergent, which means the positive and negative pieces are both going to infinity and negative infinity, but they're canceling each other out in order to actually converge. The second thing I'm going to observe is that since this thing does converge conditionally, an and thus an plus and an minus all converge to 0. Right, so that's the idea of the test for divergence, right? So if they weren't going to 0, it wouldn't converge. So since it's converging, it has to go to 0. Okay? So these are just observations I'm making before I do any work. Okay. I'm going to switch colors here. So instead of explicitly defining fn right now, that bijective function, I'm going to sort of recursively craft it and show how it's made, okay? So let me say maybe step 1, just to be clear. Let P1 be the smallest. So, sorry, I should do this. Let P1 greater than 0, strictly greater than 0. Pay attention to these inequalities, because this is going to be important. So this is strict. So P1 strictly greater than 0 will be the smallest integer such that the sum n going from 1 to P1 of an plus is greater than x. All right, so what I'm saying is add up enough positive terms where enough is at least 1, because it has to be a number strictly larger than 0 that's an integer. So I'm adding at least one term, but as many as needed to be bigger than x from the positive list of numbers, okay? So if x is -7, then adding any number of positive numbers makes it bigger. So this P1 would be 1, because it has to be at least 1, and the first time I sum anything, even if that sum is 0, I'm still going to have 0 greater than -7, so I'm done, right? But if I picked x to be like 684 billion, and this was the alternating harmonic where I'm adding a bunch of, progressively smaller fractions, then I'd be adding up a whole lot of terms here, right? Because I'd have to add up a whole bunch in order to get that big. So this is what this is saying. Just get bigger. We don't know how much bigger, but bigger. So in particular, what I'm saying here as well, just again to be clear, is if I did n equals 1 to P1 minus 1, so if we assume for a second that P1 is bigger than 1, and I added up that many, I would still get something smaller than x. And as soon as I go to the correct size, this thing is bigger than x, right? So again, if it's 1, this doesn't really make sense because I'm going from 1 to 0. So if we sort of discount that particular part of it, this is what we're doing. Moreover, I'm going to take this thing and I'm going to denote this, so I'm defining it to be A1. And we'll see why I'm going to do that in a little bit. All right, step 2. So now I'm going to let Q1 greater than 0, again, strictly, and again, be the smallest integer, such that, so here I went bigger than x. So what I'm going to do is I'm going to take whatever was bigger than x, which is the value I had, the A1, and then I'm adding the negative piece of it by doing n equals 1 again to Q1 of an minus. So these are negative things I'm adding. I'm going to add negative stuff to a value that is bigger than x until I get something that is smaller than x. Okay? And I'm going, so again, same idea as here, right? If I did one less, I'd still have something bigger than x. On that 1, I have something that is less than x. And I'm going to define this thing, that value, as A2. So A2 is this piece here, this A1 plus that negative sum that's now less than x. Okay? Step 3. So now I'm going to let P2, so now I'm not going to be greater than 0, I'm going to be greater, strictly greater than P1. Again, strict. This is actually important. So I'm just going to write this little quote here, be the smallest integer such that. Now I had A2, which is now smaller than x, and it's adding these terms up, so I'm going to get A2, so let me do it this way so it's a little clearer maybe. So I'm going to take A2, and eventually I'm going to want something bigger than x. So I'm going to take x to be smaller than A2 plus the sum n equals P1 plus 1 to P2. So essentially what I'm doing here, because P2 is strictly bigger than P1, this is okay, right? Oh, might help if I actually write the rest of it, huh? So what I'm doing is I'm taking that A1 piece that I had here, and I'm continuing it. So I added up to P1, so now I'm going from P1 plus 1 and continuing on, adding positive things until I get bigger than x. And this, again, I'm going to define as A3. And the sort of last step to show this recursive relationship, step 4, I'm going to let Q2, again, strictly bigger than Q1, be the smallest integer such that. And now I'm going to, again, do the same idea here where I'm going to have x be bigger than the result. So x is larger than A3 now, plus the negative piece that I'm going to be tacking on. So this is, again, in the same idea. I'm going to continue where I left off up here. So I'm going to have n equals Q1 plus 1 up to Q2 of an minus. Okay. I'm just going to write etc. So this is how I'm going to do it. I'm going to keep tacking on terms in this alternating order, right? I'm going to keep tacking on some positive pieces and then some negative pieces. And so the idea, if you want to think of this maybe as some sort of discrete graph, like some sort of graph-looking thing, is I have my sort of goal value of x, right? When I add the an pluses, I'm going to keep going until I go just past this value, right? And this would be some like P1 or something, right? Where this is the partial sum. So it goes up just past x. Then I'm going to subtract off as many things as I need to get just below x, which just below is relative. Maybe it goes up really high, maybe it goes sort of not as high, although we'll talk about that. So this would be maybe Q1, right? As where adding one term went from above to below, went from here to here, right? And then the next time I add, I'm going to go up until I'm just past again. So I'm going to go up to P2, where again, down here would be like, down here would be something like P2 minus 1. The sum of P2 minus 1 would be like just below the line. And when I add up to P2 terms, right, I'm above the line. And then the next time I go down, I'll get maybe to Q2, same idea. Okay. So the idea, the hope, which I have to prove still, but the hope is that I'm sort of oscillating around this line, but as I do that long enough, I'm going to get closer and closer to sort of leveling out on the line and have a sum that hits x. That's the dream. Okay. But first and foremost, I want to show that this is, so claim that f from natural numbers to natural numbers be the map such that. So here I'm adding terms up, right? So I'm add from 1 to P1 of an plus, then I add m1 to q1 of an minus, then the next up to P2, right, from P1 plus 1 to P2, an plus terms again, then these, right, so I'm oscillating which ones I am doing. So if I denote the new series I get, denote the rearrangement, and I'm going to put this in quotes, because I don't necessarily mean rearrangement in the sense that I know this is bijective, I'm about to show that. So by rearrangement, I mean colloquially. I'm back, okay. So sorry about that, the audio died, and thankfully I caught it after only talking for, a few hours now. But so weird cut in there while I mess with the audio and get it working again. Okay, so I'm not entirely sure when it cut off. So I might have some notes in the doobly-doo down below, the little description in the video to fill in anything missing. But I think where I got cut off was saying that I'm going to, so here I have the the new way I'm ordering things, right? Like up to the P1 of the first things, then up to Q1 of the negative ones, then the next up to P2 of the positive, etc. So I'm going to call this rearrangement Bn. I put rearrangement in quotes because I mean this in the colloquial sense. I'm about to show that this is a mathematical rearrangement in the terms of that bijective function. So right now I'm just saying that whatever this mess is that I've written, it should be clear from here which term is which, meaning if I want to look at B7, I would look at, is P1 big enough, P2 big enough, etc., Q1, Q2, figure out which of the ANs it is, and put it in, right? So if the seventh term was a positive thing, then it would be an AN plus. If it's a negative one, it will be an AN minus, and I'd figure it out from there, right? So it should be sort of clear what the Bn definition is, and that I'm doing some sort of, in common terms, some sort of rearrangement of AN. So now I want to show that it actually is. So my claim is that I'm going to let Fn, f from n to n be the map, be the function, such that such that a sub f of n equals Bn. Then my claim is f is a bijection. So I'm going to sort of mostly explain, but show some of this. So in particular, notice that both Pn and Qn, so these are integers. P1 and Q1 are both strictly greater than 0, so they're at least 1, right? But P2 and Q2 are strictly bigger than P1 and Q1. So if P1 and Q1 are at least 1, these are at least 1 bigger than that, so these are at least 2. In particular, for any given n, Pn Qn is greater than or equal to n. Probably much greater at some point, but it is at least n for each of these, right? So, since we're oscillating between these things indefinitely, right, infinitely many times that we go back from one to the other, as I use up infinitely many Pn and Qn, i.e. as n goes to infinity, n increases to infinity. I'm writing this in shorthand because I don't have a lot of room. If this were a real proof, you would write it out with real full English sentences. So as n increases to infinity, so does Pn and Qn, i.e., which is to say that since the Pn and Qn, which is how many of the positive and negative terms I'm adding together, those go to infinity. So I'm adding together infinitely many. I'm adding together all of the terms. So, i.e., all terms of an plus and an minus, right? Because I'm using them in order, n to q1, q1 plus 1 to q2, right? I'm not skipping any. So all of these terms are used. So in particular, or I guess I should really say not in particular, because it's not a sub-example. So thus, an are used. Therefore, f is surjective. Or I guess maybe with the way I defined f, it might be the inverse might be surjective. But the point is that I'm using all of the things. So I guess f is defined on, it is well defined on all of n, because every element goes somewhere, okay? So every element goes somewhere. We're using up all of the ANs. But more than that, For any given an, right, if I look at a5, if a5 is positive, right, and remember assuming that none of them are 0, so they're either positive or negative, I don't have to worry about 0 being some sort of annoying overlap. So if a5 is positive, then I'm going to find it between one of these things, right? So if P1 is 2 and P2 is 7, then my A5 is showing up right in this sum, right? Because it's adding up from 2 plus 1 is 3 up to 7, so A5 is here, right? Meaning that all of the ANs are actually used, but they're only used once, right? Because if it's A5, I know exactly where A5 is. It would be here, right, if it's the positive thing. It's not here and here, or here and there, right? So it is surjective and injective, i.e. bijective. So I'm doing a little bit of hand waving at the end. I would encourage you to flesh that part out if you'd like. The formal way you can do it is to assume that you have, a sub fn and a sub fm are the same thing, the same, ak for some k, and then show that n equals m. That would be the sort of very rigorous way of doing it. Okay, despite my jumping around a moment ago to fix sound issues, I'm going to do some editing magic here because it remains to show. All right, so I sort of showed, I'm claiming I have shown that this rearrangement is a rearrangement. I have something that is bijective, but it still remains to show that I honestly do get a sum that equals x. So that's what I'm going to do next. So I'm going to do some editing magic and get rid of all of this and then do that part. So abracadabra. And we're back. All right. So I erased all the stuff and I recalled a result from before. I realized with the way I sort of defined it, it's hard to say Bn is a certain thing. So I recalled this in terms of an pluses and minuses. I would encourage you to check your notes or rewind the video a little bit and take a look at what I'm saying here to make sure you understand fully, because what I'm about to do sort of relies entirely on this relationship. Essentially what I'm saying is that up here, the difference is that I'm adding up to pk minus 1 versus pk. So if I go one index shy of the full pk, then I'm going to be less than x. Adding that one more positive term gets me bigger than x, right? Because remember, when we're adding the pk terms, the an plus terms, we're getting just past x. And the k index for the q's is smaller, so I haven't gone back down yet. Because you remember when I did p1 to get past, then q1 to get under again, then p2 to get past, too high, then q2 to go under. So I haven't gone back down yet, so that's q sub k minus 1, as opposed to p sub k minus 1. So where those negative ones are makes a big difference, okay? The other thing is that if I do add the full up to pk and up to qk, that means that I went up to pk, but then back down with qk, so I am just under x. Whereas if I went one less in the negative direction, I would be above, okay? So the two sort of situations here that I'm talking about, again, if this is x, then if this thing is, say, A1 versus B1, what I'm saying here is that this difference is showing the on the rise part, where here I'm at A1, and then I add one more piece to get to B1. So this is adding that one A sub pk plus jumps to be over the value of x. Whereas down here, what I'm saying is, again, if this is x, I'm now looking at the other direction. So if I look at going down, over here is where I am at the part that is still bigger. So this is, if I did say A2 is this side and B2 is that side, now I'm sort of in the other direction, or different relation. So here B2 is still the one above, A2 is the one below, and adding this piece is the plus A sub QK minus, right? So I'm just reminding you that adding the one more term when I'm adding to the Q sum gets me lower than X. Adding one more term when I'm adding to the P sum gets me bigger than X. That's what I'm trying to point out here, okay? All right, so my goal is to show, so I want to show, just to remind ourselves, that the sum of Bn, where Bn is the rearrangement now, that this actually equals X, okay? In particular, or sort of suffices to say, or that is to say that I want to show that the limit as n, as capital N goes to infinity of the sum n going from 1 to capital N now of Bn minus X, that this is 0. Okay? Okay. So to this end, fix capital N wherever you want. Okay? This would be slightly easier to show in some ways if I fixed the N to be one of these PKs or QKs, but then there'd be some other stuff I have to show other than that. So instead, I'm just going to say fix N wherever you want. Okay? Sorry, editing magic again. The technology is not entirely with me today, it seems. So, sorry. So fix N wherever we want. All right, so now notation's going to be a little annoying, but bear with me. I'll draw a picture that will hopefully make it clear what's happening. So let K1 be the smallest index. Sorry, not smallest index. I want the largest. Be the largest index such that. So remember what these BNs are, sort of the PKs, then Q, the like PKs, then QKs, then back and forth, right? So it's up to P1, then up to Q1, then up to P2, then up to Q2, right? And Bn is sort of just tracking all of those. So I'm going to pick the largest index such that P sub P sub K1 is less than or equal to N, capital N again, N less than or equal to P sub K sub 1 plus 1. So basically, I'm going to pick, I'll draw a picture here, but I'm picking basically the one that happens before, so I guess on this one, the earliest one that happens while it's still going positive before I hit wherever N is. I'm also going to let K2 be, again, the largest index such that Q sub K2 is less than or equal to N, less than or equal to P sub K2 plus 1. Okay? So essentially what's happening here, again, is that I have some, all right, so that I can draw one picture nicely, let me do this. Case 1, let's just say that K1 is greater than K2. I'm sorry, I messed that up. These should be f of these things. Yeah, sorry. I want them to be the thing where these things went. So f of p sub k1 plus 1, f of p sub k2 plus 1. All right. So if I'm assuming that K1 is bigger than K2, what this means, so again, I'm going to draw the picture, which I keep threatening to draw, so now I'm going to draw it. Again, we have the line X here. We have a running sum, so I'm going to draw the running sum like I've been doing, and the running sum is going up, down, etc., right? So if K1 is bigger than K2, that means that I am the increase, the p sub k's, the adding positive values, is happening after the K2. So that means that I'm going up before, after I'm going down, which means that I might have some n, say, here. Yeah, let's say I have n here. This top part then, this is the f of p sub k1, and down here is the f of p sub k2. Running sums, so this will be, see, I'm trying to make it simple and it's not simple, and so it's, sorry, I'm just making things worse, so let me do this. So the right graph, the right points, I'm just gonna write them elsewhere. So if this is, say, point A, point B, and point C, then what I'm looking at in this case is that the sum, so A is actually the sum, n going from 1 to pk1 an plus, that's actually k1 minus 1, plus the sum n equals 1 to pk2 minus 1 of an minus. So I'm basically at this point, this A2, down here, okay? This one then adds another up to p, right? It gets rid of this subscript bit here. So B then is the sum, and going from 1 to pk1 an plus, sum n equals 1 to pk2 minus 1 an minus. And point C is my actual goal, my sum up to Bn, to whatever that index is, which was labeled capital M, okay? So in my case 1, that K1 is bigger than K2, what I'm saying is that I am past the top of the curve here, right? I'm coming back down, but I'm not so far that I've started going back up, because then my new lowest point would be over here, not over here, okay? So what I'm saying is the lowest point, as I'm doing a running sum, happens before the highest point, before my actual index, okay? But remember, this value here, just like up here, is really just the last term it took to add to get above x, right? So that means that my C is going to be somewhere between whatever the distance was that got me above, right? And whatever the distance is that gets me down below this thing, from here to there, right? So in this case, I have that my sum, n equals 1 to n. I don't know why I'm doing k now. I have to redo this part of the video because I feel like I might have lost some of you, but we'll see how it goes. So this thing that I'm trying to figure out, so its distance from x, so minus x, right? This distance from x here up to c is going to be on either above x, in which case it's smaller than the distance of my last term here, right? So it's going to be either smaller, so if it's above, right, if it's more than x, it's going to be smaller than whatever that distance was, which was a sub pk1 plus, right? Or if it's below, it's going to be, right, if it were below the line, like down here instead, then it's going to be smaller than the distance from here to the bottom to x, which was the last thing I would have added in order to get to the next downward hump, which would have been pk2. So this is positive, but just to be clear, I'll make it absolute value. So this is qk2. qk2. So depending on where it is, it's either less than that value or less than that value, which means it is certainly less than the max of those two values. Okay? Did I mess that up? I did mess that up. I don't know if anybody caught this, but these should be q's. Right? The a minus is q's. All right, so either it's up here or down there. If it's up here, it's less than that number. If it's down there, it's less than that number. So it's definitely less than the max of those two. In the case 2, where instead I have that k2 is the bigger thing, what does that mean? Well, that means that I have some situation like this, only now instead of being on the down slope, it's going to be on the up slope, right? So instead, I'm going to have something that looks like, maybe I'll draw a different set over here. So instead of being on the down slope, I'm going to be on the up slope, which I'll draw just so it's hopefully more visible. I draw it over here. I have something like this, where this is the c, it's on the up slope. But now, if this is going sort of down to a value, up to a value, down to a value, the first thing, like the earlier, or the rightmost bottom part here, this is the sum up to the qk2, right? So this is the sum qk2. This is the sum for the pk1. So I'm going to basically make the same sort of argument, is that this now is the sum pk1 plus 1. So if I'm on the positive side, if I'm above x, then I'm above x by 1, no more than this n bit, and plus the last term of that. So it's basically going to be the exact same argument. So this is the sum 1 to n bn minus x less than or equal to max in absolute value. So if I'm on the positive side, it's going to be the last thing added here, which is a plus, and it is the pk1 plus 1. And if it were on the negative side, then it would be barely negative, right? Because this is the last sum over here, which would have been a qk2 minus All right. So this is the alphabet soup part of the proof, which is a little annoying, I grant you. But the important thing to take away is that it essentially can't be too far away from x because I only ever hop the line by one value, right? By one piece. Either the qk2 because I'm going underneath, or the pk1 because I'm going above, right? Plus or minus a 1, depending on where exactly I am. But if you recall, an plus and an minus both go to 0 because an goes to 0. So in particular, the max of the two also in limit goes to 0. So the limit as n goes to infinity, sorry, the wrong symbol, of x minus the sum, n equals 1 to capital N of Bn. This is less than or equal to the limit as n goes to infinity of the max of really all of these things. So I can just say a p k1 plus 1, a q k2, and a p k1. But the limit of those things is 0, right? So obviously it's an absolute value, so it's greater than or equal to 0, but it's also less than or equal to 0, so it equals 0, and then I'm all set, okay? Okay, so that one was hopefully not too confusing. I mean, on the one hand, the details are important, that's the whole point of rigor. On the other hand, the details are sort of messy and hard to write down. It's one of those, again, intuitive proofs that when you try to write down, it gets a little messy. So the intuition part is that since we only ever hop over x in either direction by at most one term, and those terms are going to 0 because this thing converges, that tells me that the amount it can jump up and down from x, the amount it can deviate from x, is going to 0, and thus the limit is 0. Okay? All right. So that is Riemann's rearrangement theorem. Probably one of my favorite theorems in terms of result, not so much with the proof, but probably one of my favorite theorems in this section, just because it really drives home that this whole idea of conditional convergence is really a balancing act between the negative pieces and the positive pieces. And it's such a delicate balance that you can sort of look at it funny and change the order just a little, and suddenly you can get any kind of ratio, any kind of number that you want from those positives and negatives, which is just fascinating. All right, so with that, we are done. Ta-da!